Now, I leave the floor to Jörg Conradt, who is an associate professor here at KTH, working with neuromorphic computing and spiky neural networks. Thank you for being here.
Thank you, Jona, for the invitation. Thank you for coming to this talk as well. I know you can't really leave now. I'm very honored to be here because I feel extremely exotic. I work on neuromorphic sensing and computation. So this is brain-inspired computing, and I'll talk about that for the next 20 minutes. And I've kind of secretly sneaked in for future space applications so that there's at least some link to the workshop. Now, I think there's more than just a little link, but really I have no understanding of space applications today, and we're only slowly getting there. So I have a research group working on neuromorphic computing. That's 3 PhD students, a number of master thesis or amanuense students, so working students, and myself. I started here 5 or 6 years ago, and there's much more to explore. So if you're nearby, come by the lab if you want. We care about brains for robots, brains for machines. So we try to build smart intelligence for everyday devices. I know you all have your robots with you. You have your machines here because they're everyday devices. But at least people talk about turning robots into everyday devices. And we're missing largely this to get robots into everyday devices. And I think if we switch this picture for a satellite, then there's probably a reason why I'm here. I'm happy to talk about how possibly to get brain-like intelligence into energy constraints, autonomously acting systems. So what is current machine learning, current AI? We all know this. We heard neural networks about 7 or 8 times in the previous few minutes. I'm sure you all know what neural networks are and how they work from layer to layer computation, from input to output. These neural networks do great. They solve amazing tasks, but they come with a price, and at least the price can be named in dollars. It comes for a heavy price tag when you want to train large language models once. Okay, this number might be outdated as of today. If you read news today, there was a big news that some Chinese company claims that they can do it for, for this, only $10 million to train your large language model. But I don't think anybody here would like to train your own large language model tomorrow, because still this is a pretty hefty price tag. And it needs a lot of energy to train these spiky networks. You need a lot of data, a lot of processing time. Here's a diagram that I found a while ago, and I think this is really impressive. This has nothing to do with neural networks per se. This is the most intelligent computing device, algorithm system at the time. So 60, 70 years back, there was a very, very simple learning system in a computer that was the most intelligent. And then there was some linear increase in logarithmic time. So there's a logarithmic increase in complexity of computing systems. But in the last decade or so, this has really increased drastically. So we are asking for more and more and more and more computing time to solve problems that we take for granted nowadays. We interact with ChatGPT, and we think it's for free because some giant companies like ChatGPT X or whoever puts up resources for us, and we rely on those resources. The brain does it very differently. All our brains are computing machines. So that's why I care about neuromorphic computing. The brains are computing machines that really are optimized to save energy and still behave and process as good as possible. So I would like to understand the computing architecture in brains and what is different to our silicon implementation and to our models of how computation work in these machines, so that we can ideally build more energy efficient, more smart computing systems one day. And now this might make a bit more sense, this picture from the last page where we're saying we would like to put brain-like computing into energy-constrained systems. So let me talk a bit about how the brain does it. I usually take these slides when I talk to computer science students. I spend 20 minutes just about the next 3 slides. I have to rush really fast through here. We know the brain is in the top of our head. We have a large number of neurons, and there's more and more neurons coming. There are also neurons dying all the time. So in my age, they're dying like now. That's how fast my neurons die. And that means my computation has to reconfigure or reshape somehow. Again, in my very naive view, that's probably similar to when you have computing infrastructure in space. They might suffer from radiation or from other effects that cause changes, unpredictable changes, just like neurons in my brain. And the way my brain computes, we can still handle that. How do neurons compute? Very different to artificial neurons. Real neurons integrate incoming energy, reuse energy, and use that to produce new signals. The signals are spikes. There's a binary, all or nothing information. So neurons communicate by sending pulses. This is very different to today's computers. Let's not go into details. But you heard about these two fundamental differences. Neurons work very unreliable. At relatively low frequencies, they integrate incoming signals and use the energy that's coming in and propagate that to generate new output signals. There's a diagram of neuron count per animal species. So we see there's some animals with very few neurons and some with very, very many neurons. There are many interesting aspects here. And again, you can find videos of me talking about small animals and large animals. What we might find interesting here is that in an area 10 to the 6, 10 to the 7, maybe 10 to the 8 neurons, we can easily simulate that many neurons in a computer. Not my laptop, but a reasonably fast computer. We still don't have machines, robots that are as flexible, as universal as mice or cat, that can adapt to vastly different environments, that can change their whole way of life. So the way how all these neurons produce behavior must be fundamentally different to the way we program our computers today. So what are the key elements that people have identified as neuron-like computation? Well, there is this fact that we have spiking neurons. I mentioned this many times. So a neural network does not compute layer by layer by layer in a sequential manner, in a framed and parallel manner. Instead, spiking neural networks produce events every once in a while, forward those, and only when there is a spike, the yellow dot arriving at the next neuron, we update information, and that's the only time when energy is needed for computation. So most of these neurons, especially in the later layers, they're pretty silent. They don't compute and they don't activate at all. So on your GPU card, you would still have to crunch through these neurons over and over and over again, because that's the way how GPUs work. But if you begin to think that we can implement such neurons in dedicated silicon that integrates incoming charges, incoming energy, and only activates at all when there is a spike coming in, then you see how such a network, such a spiking network, can be significantly more energy efficient than a standard neural network that computes all layers over and over and over again, because you get this synchronized parallel input. That's one aspect, spiking computing units distributed. When we think of networks, here you see a traditional neural network. When we think of neural networks, we usually talk about layers and layer after layer activation. That's not how our brain works again. Our brain is composed as what we call a small world network, where we have dense local interconnectivity and very sparse long-range connectivity. So there's a lot of happening locally and very sparse activation going long range, because sending information long range is costly. You want to keep as much as local as possible. Same for learning. We're all used to backpropagation learning and spiking neural networks. So we have a global teacher signal that backpropagates and produces error messages throughout the network to change all of the network, all the weights, all the parameters. Instead, our brain largely relies on local learning, so that learning only happens within one of these local regions of our network, which again saves a lot of energy. So these are algorithmic concepts of neuromorphic computing. There's also a hardware side to it. People begin building specialized computers, special computing systems that naturally match such computing ideas or such connectivity ideas. We do no longer need a separate giant memory and a very fast processor that talk and interact, but instead we begin to intertwine memory and computation, because every single neuron is local or very long range, very short range, very nearby, computing only. So we can design dedicated computing hardware that is optimized for such processing and again saves energy when computing. Oh, there's an expert, Arvind, who's also working on event-based and neuromorphic computing.
I heard you. I had to come and stop.
There are also appropriate sensors. If you think of video cameras, they produce image after image. Well, once you have a whole image full of colors, then you're back at this neural network layer by layer, full processing. Instead, we talk about event cameras. I'll give you more examples about event cameras that work like our eyes work, which only send changes into the brain. So we are so used to cameras, we think we have cameras in our head, but actually we have photoreceptors that measure incoming light, photocurrent, and only when there's a certain change, the photoreceptor gives a signal into the brain, and my brain reconstructs the world. So my eye does not tell the brain, oh, table, 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 all the time. That would be an overflow of information. It would be intensely expensive to compute on that. My eye says table or black spot, and I reconstruct table once, and then my brain remembers, oh yeah, the table is still there. So we have cameras that work on such principles, which produce point clouds of changes over time. So where has something changed? And we get this information in at very, very high updates rates at very low energy cost, because we do not have to represent redundant image information over and over again. All these are ideas and concepts of neuromorphic computing, of neuro-inspired technical systems. That's what the field does. Now let me give you some more examples about hardware and about algorithms. So when people today talk about neuromorphic engineering, they mainly mean hardware, building computers. That's not what we do in my lab, but I'll give you a brief overview so that you have a better idea of what's happening. I've already said it's different to laptops, to computers. In a standard computer, we have a processor that's very fast, gigahertz, and we have some memory, and those interact and shuffle information back and forth. Very costly. In a GPU, the system is slightly different, where we have a parallel processing architecture that runs the same algorithm. And there's still some memory that might be closer or further away from the GPU. But again, it's a system that is composed of processors and separate memory and shuffles data back and forth. In Neuromorphic, we build processors that locally have their own little memory block and their own little computation, and that have a certain communication infrastructure. Here is one giant data bus, very big, very fast, that moves information from the processor side to the storage side and back and forth. Here we don't need such, because processing and memory is typically intertwined. A single neuron knows what it needs to know locally and sends only a very sparse information, saying here's a spike as a message elsewhere. And that's what other neurons receive and process. So we can save on computation energy. This is an overview of existing neuromorphic hardware that you can go and buy today. If you say, oh, that's a great idea, I want to get my own neuromorphic computer, you can run neuromorphic algorithms on as standard systems as CPU and GPUs, but you can go all the way down to customized chips and build dedicated special hardware. There are companies, I'll show you on the next slide, that offer such as service. There are prototypes, mainly from universities or large research labs like Intel, that build neuromorphic development platforms. So all of these are generic. You can configure more or less many parameters. So you can change them to compute your network, but you're limited to neural style communication, neural style type of computation. They're very efficient for that. This is your industry portfolio today. If you go out, you can either talk to big companies like IBM or Intel, and get a neuromorphic computing setup. It's a bit like a quantum computer. If you have enough money, you can buy it. You can talk to academic players. There are many test boards, development systems, which can easily be used to run your spiking networks efficiently. There are also many smaller companies. There are startups for computation, and there are startups for sensors. So you can get hold of these devices, of these systems, if you want to build an energy-efficient neuromorphic computer. In fact, this company develops IP And a very big Sweden-based space company has recently teamed up with Aikida to develop hardware, computing hardware that they can send into space that is potentially very robust against radiation and other effects. So we have a common project starting on what to do with that hardware. So that's my point of contact into space. Now let's spend another 5 minutes talking about algorithms and what to do with that. So we have a lab, I said someone here before, we have a lab just in the next building where we build some electronics and we have a robotics area and we have lots of different robots because I care about interacting systems, about behaving systems that sense and act in the world. Here's an example. There's a walking robot dog, and that robot dog, you've probably seen videos like this from Boston Dynamics with a big dog, and when they move, they always move like this. The reason why they move like this is because dynamics is difficult. It's hard for any robot to walk like we humans walk. But walking like this comes with a price that the camera head is shaking all the time. When the camera head is shaking, this is what your camera sees. It's very, very hard. It's very expensive and very difficult, challenging to do computer vision. Now we have these event cameras, and the event cameras produce changes when the robot wobbles and walks, and we can interpret these changes and recognize objects. I can play this again, and we can much easier see what is happening here. And the reason why this video also looks a little blurred, this is a stereo view from the robot head. The reason why this video looks a little blurred is because we have to bin events in time to reproduce a video that we can see. In reality, these events, the green dots, they come at perfect time. They come asynchronous as spikes, as input into a network. And we have processing networks that can take this as input and extract find objects, do tracking, do localization at very low cost, significantly cheaper than we could do in standard computer vision, and let's say YOLO, even on clear, non-blurred images. That's one project. Here's another example project where we have a human interacting with a robotic arm. So a human can hold tools, heavy items maybe, and there's a camera system observing that object and tracking that object at extremely low latency, so the robot can follow the human very, very fast. Here's one more example project. We can go in a little deeper, where we want to track traffic participants. It happens that this is a Digital Future co-funded project. So let's assume you work for Stockholm Stad, for the city of Stockholm, and you want to observe traffic in the city. Of course, you can mount cameras on all the traffic lights and have a computer at every traffic light that extracts cars and bicycles and pedestrians and gives you information about traffic in real time. It's not a big problem except for costs today. It's very expensive to build cameras and computers everywhere, and for energy consumption. When these run 24/7, they consume a lot of energy all the time. Not to mention data privacy, GDPR aspects, so we'll see. So we have a project where we want to track all these traffic participants, including bicycles and people, with this event camera and a spiking neural network because it's energy efficient. So what we have done is we've created a data set by regular camera recording and an event camera recording simultaneously. So to create our input data set, we have two recordings at the same time, same field of view. You see real cars and you see the events coming in from that change camera. Now we can use standard computers to label this. We run standard YOLO or some other algorithm to label our data stream once. We have 300 hours of recordings, we label them. Now we have labeled data. We can move these labels into our event stream. That's what you see here. So now we have a labeled event camera stream. And we use these labels to say, okay, somewhere here's a car, somewhere here's a car, somewhere here. So we produce a desired spiking neural network output. What we do then is we take this desired output, we take the event camera only input, we train a spiking neural network. We're saying that's your input, that's what you should produce. Please produce an output where you spot the cars, where you tell us where are cars. So once this is trained on our data set, this is the output from the neural network. You see it's a little different from the ground truth, but we're getting pretty good tracking results. And we're in the process of assessing the energy consumption of this, but it is about 2 orders of magnitude smaller than this. So now we have an embedded box that contains an event camera and a very small processor that runs a spiking network because it's very efficient on neuromorphic hardware. And we can track, for example, cars. We're in the process of extending this to other participants, bicycles and whatnot, and reducing the complexity of that spiking neural network. So here is a project where we apply spiking networks and event cameras in a low power autonomous setting. Details we can look at. I think there's the robot dog again. I already talked about that for some time, so I don't think we need to go in more detail. That's what I want to communicate in my 20 minutes. So again, I'm not a space person. I'm exotic here, but I'm interested in energy efficient computing. What is the most energy efficient computer we know of? It's our brain. So we want to understand in my group, we want to understand how brains process information and convert the ideas, the principles of how to process information into technology. So we build spiking networks, we build brain-inspired computing in my lab, typically for low energy, real-time, closed-loop motor systems. But this could be a sensor, this could be an observer as well. And I think there's a lot of potential for this neuromorphic computing, for this type of information processing, especially in low energy scenarios. Thank you for the interest. And I'm more than happy to take any questions now or during coffee.
Quick question. Fantastic. It's the first time I hear about those things. Can we, without having neuromorphic hardware, can we benchmark and compare the different methods that have current, or is it a very unfair comparison?
We can benchmark without having neuromorphic hardware. So in fact, in my lab, most of the work we do is we work on standard GPUs. They're beasts, they're brute force power, but then we have these power outlets. And in my lab, we don't care about power consumption today. We develop fundamental algorithms that we know because of the computing principles will work very, very low energy. You could do a theoretical comparison. You could say, okay, my neurons spike this many spikes per second whenever on average in a network. Whenever I have a spike, I need this much energy on a computer. I know my GPU computes everything all the time brute force, but I would really only need to compute 1% of the time. And that's in fact something we do. So we look at the GPU activation and we see how many of the CUDA cores compute just 0 because that's what they do, and how many of them have actually numbers and meaning to compute. And it turns out we usually use about 3 to 5% of the CUDA cores as activity. Then again, we have to compare how good are we. So today, almost all the algorithms, almost all the examples achieve lower precision, lower accuracy, lower performance, if you want, compared to high quality video cameras and big computers. But if you get 80% of the correctness at 5% of the energy, there are application areas where this is needed. And in fact, this is how all of us work. Yeah. So, yes, please.
No, so I was just, maybe this is far-fetched and not possible, but I was wondering, do you think that this type of sensors, like relating maybe to the talks also this morning, could be used to look at the sun? So I think it would be very handy to have something that kind of detects only when you have some spiking activity, like a flare or something on the sun.
So these sensors have been used to look at the sun, to look at the eclipse, to look at whatnot, because they have a very high dynamic range. I have only had 30 seconds to talk about the sensors. The principle again is that every pixel is an asynchronous camera in itself. It does not integrate over a window of time, but every single pixel only looks at the current incoming brightness, the momentarily incoming photocurrent. And therefore, we can simultaneously see into dark areas and extremely bright areas and get high contrast images. So yes, people have even put them on satellites and sent them up in space to look out and in back to Earth. Not my research. There's a group in Australia that does it. People have used these for sun observations. There's a pretty big upcoming hype in computer vision about these event-based cameras. You can Google that, and there's an explosion in work and publications.
Adelaide University?
Sorry, Tyler?
Is it Adelaide University?
No, it's a University of Western Sydney. Greg Cohen. Yes, and
So you mentioned the power consumption is orders of magnitude lower compared to rate-based. But how about the inference time, and is it compared? Is it so intense energy?
So you asked about latency or inference time for the networks because it's low energy. So let me state this correctly. This type of information encoding, spikes versus regular images, constant data vectors or tensors, uses lower energy. It's not rate-based. If I use spiking neurons to represent rates, then I just have a different form of representing tensors, and that's extremely inefficient. So it's a temporal spatial encoding where we have individual spikes. The latency can be tuned in the networks. We can get very low latencies, typically a bit higher than standard vision networks, because a standard vision network works that you have an image, you compute layer by layer, and you get your output. In a spiking network, it takes a little time to build up information in each layer. So typically it takes 2 or 3 times the whole propagation delay. But you can tune for those and have a trade-off between speed and energy and precision. So one more quick, or should we move on?
It's quite fast. For the specialized neuromorphic hardware that you have shown, do I need to change the way my classical, like fluid dynamics or any other application works to make it run there?
Yes, and that's a very that's a very important observation. So you have to completely rethink your algorithms. It's a completely new way of modifying information. That's what computation means. You take some information and you change it to get some other information. You have to completely rethink how to process information. That's the main research in my lab, where we think about how to handle such spiking processing.
But could I expect the performance in this neuromorphic hardware to be better than in GPUs or in CPUs?
Better is a difficult term. You can expect it to be on lower energy. It might be faster, it might be slower, it might be more correct or less correct. Today, I have no reason to believe that I will be more correct than YOLO. Tens of years of research has gone into YOLO. Computer vision is a field that's 50 years old, and hundreds of thousands of researchers have worked on it. This is a very new field. It's 10 years old, 15 at most. There are probably 100 groups worldwide working on neuromorphic computing. It's a very young field. So today, we cannot outperform per se any existing algorithms. There are niche areas where we are extremely fast because of the camera, extremely efficient because of the chips, something like that. But we are not better, more correct. We don't find one more car in an image compared to YOLO. No, we don't.
We need to move on.
Thank you so much for your interest.